Behavior of tall buildings using tuned mass dampers. Abstract incalculable elevated structure has been built everywhere on over the world and the number is expanding step by step. This isn't just because of worried over high thickness of populace in the urban communities, business zones and space sparing, yet additionally to build up landmarks. As the seismic burden following up on a structure is a component of oneself load of the structure, these structures are made similarly light and adaptable, which have moderately low common damping, and in this manner the structures become more vibration inclined under wind and tremor stacking. To guarantee the useful execution of tall structures, different plan adjustments are conceivable, extending from elective basic frameworks to the use of inactive and dynamic control gadgets. This paper presents an outline of cutting-edge measures to lessen basic reaction of tall structures, including a conversation of assistant damping gadgets for moderating the seismic tremor and wind-initiated movement of structures. To guarantee the useful execution of tall structures, different plan adjustments are conceivable, running from elective auxiliary frameworks to the use of aloof and dynamic control gadgets. Latent tuned mass damper, TMD, is broadly used to control auxiliary vibration under wind load, yet its viability to lessen tremor-initiated vibration is a developing procedure. Here an investigative examination is proposed to contemplate the adequacy of TMD to decrease auxiliary vibration in tall buildings. For this examination a 60m tall structure having 15 stories with a square arrangement of 20x20m has been displayed. The viability of single TMD to lessen basic vibrations is read for a variety of TMD mass proportion. Keywords: structural motions, damping, passive and active control devices, TMD, AMD. 1.1 Introduction. Vibration might be brought about by natural powers following up on a structure, for example, wind or earthquakes, or by an apparently harmless vibration source causing reverberation that might be ruinous, terrible, or basically badly arranged. The seismic waves will make structures influence and waver in different manners relying upon the recurrence and heading of ground movement, and the tallness and development of the structure. Seismic movement can cause extreme motions of the structure which may prompt even auxiliary disappointment. The power of wind against tall structures can make the head of high-rises move significantly in excess of a meter. This movement can be through influencing or winding. Certain points of wind and streamlined properties of a structure can emphasize the development and cause movement infection in inhabitants and posture genuine functionality issues. To upgrade the useful execution of the structure against seismic and wind powers, an appropriate structure configuration is performed utilizing elective basic frameworks and by usage of different vibration control equipment. 1.2 Tuned mass dampers, TMDs. TMDs being used, ordinarily oil dampers, thick and viscoelastic dampers. Normally, a TMD comprises of an inertial mass appended to the structure area with most extreme movement, by and large close to the top, through a spring and damping component, ordinarily gooey and viscoelastic dampers. The recurrence of the damper is tuned to a specific auxiliary recurrence, so when that recurrence is energized, the damper will resound out of stage with the basic movement. Vitality is disseminated by the damper dormancy power following up on the structure. The adequacy of TMDs is dictated by their dynamic qualities, stroke, and the measure of the additional mass. Extra damping presented by the framework is additionally reliant on the proportion of the damper mass to the powerful mass of the structure in the method of intrigue, commonly coming about in TMDs, which weigh 0.25 to 1.0% of the structure's weight in the major mode, normally around 33%. Regularly, dividing limitations won't license customary TMD designs, requiring the establishment of elective arrangements including multi-stage pendulums, modified pendulums, and frameworks with precisely guided slide tables, hydrostatic heading, and covered elastic direction. Curl springs or variable solidness pneumatic springs commonly give the firmness to the tuning of TMDs. In spite of the fact that TMDs are frequently viable, far superior reactions have been noted using different damper setups, MDCs, which comprise of a few dampers set in corresponding with appropriated characteristic frequencies around the control tuning recurrence. Karim and Klein 1995. 1.3 Real-life structures equipped with TMDs. Tuned mass dampers have been used to improve the response of building structures under wind and seismic excitation. A short description of the several building structures that are equipped with tuned mass dampers, TMDs, follows. I. John Hancock Tower, Boston. Perhaps the earliest utilization of this sort was introduced in June 1977 in the 244m, 60-story, John Hancock Tower in Boston. Two TMDs were introduced at furthest edges of the 58th floor, at a dispersing of 67m, so as to check influence just as the torsional movement because of the state of the structure. Every damper estimated about 5.2x 5.2x 1m and was basically a steel box loaded up with lead, weighing 300 tons, connected to the edge of the structure by solid springs. The lead-filled weight slides to and fro on a hydrostatic bearing comprising of a slight layer of oil constrained through openings in the steel plate. At whatever point the level quickening surpasses 0.003 grams for 2 sequential cycles, the framework is naturally actuated. This framework is relied upon to lessen the influence of the structure by 40 to half. 2 City Crop Center, New York. Another spearheading utilization of TMDs has been in the Citicorp building in New York. The stature of the structure is 278m with major time of around 6.5 s and damping proportion of 1% along the 2 tomahawks. The framework, estimating 9.14x 9.14x 3.05 m, comprises of a 410-ton solid square upheld on a progression of 1260 cm distance across water-powered weight offset heading with 2 spring damping instruments, one for the north-south movement and one for the east-west movement, was introduced in the 63rd floor in 1978. The framework lessens the breeze-actuated reaction of the Citicorp working by 40% in both the north-south and east-west bearings. At the same time, Wiesner 1979. The damper framework is initiated naturally at whatever point the flat quickening surpasses 0.003 grams for 2 successive cycles and will consequently close itself down when the structure speeding up doesn't surpass 0.00075 grams in either hub over a 30-minute span. 3. Chiba Port Tower, Japan. Chiba Port Tower, a steel structure of 125 m in tallness and having a rhombus-formed arrangement with a side length of 15 m, finished in 1986, was the main pinnacle in Japan to be outfitted with a TMD. The time span in the first and second method of vibrations are 2.25 s and 0.51 s, separately for the X course and 2.7 s and 0.57 s for the Y heading individually. Damping for the crucial mode was figured at 0.5%. For higher method of vibration, damping proportions relative to frequencies were expected in the examination. The utilization of the TMD was to build damping of the primary mode for both the X and Y bearings. The mass proportion of the damper regarding the modular mass of the principal mode was around 1/120 in the X course and 1/80th in the Y heading, periods in the X and Y bearings of 2.24 s and 2.72 s, individually, and a damper damping proportion of 15%. Decreases of around 30 to 40% in the relocation of the highest level and 30% in the pinnacle twisting minutes are normal. 4. Taipei 101, Taiwan. Taipei 101. A steel propped assembling is the third tallest structure on the planet. A circle-formed TMD of weight 660 ton and width 5.5 m has been introduced between 88th to 92nd floor of the structure as appeared in figure 1.5. This is a case of a pendulum-type tuned mass damper. The tremendous circle was suspended by 4 arrangement of links, and the dynamic vitality is scattered by 8 water-powered cylinders each having length of 2 m. The damper can lessen 40% of the pinnacle development. Another 2 tuned mass dampers, each gauging 6 metric tons, sit at the tip of the tower. These forestall harm to the structure because of solid breeze loads. V. Burj Al Arab, Dubai. In the world's tallest hotel, Burj Al Arab is equipped with 11 TMDs have been installed at different locations to control the wind-induced vibration. 6. ATC Tower in New Delhi, India. A 50-ton tuned mass damper has been installed just beneath the ATC floor at 90 m level. 7. Statue of Unity, India. In the world's tallest statue, the Statue of Unity, 182 m high, 2 200-ton tuned mass dampers has been installed at the shoulder level. 1.4 Equations of motion. In this section, the concept of the tuned mass damper is illustrated using the two-mass system shown in figure 5. Here, the subscript D refers to the tuned mass damper. The structure is idealized as a single degree of freedom system. Hence the following notation can be defined as 1.6 Model considered for analysis. The models considered for investigation are test models and contextual analysis models. It has been endeavored to choose models which are both delegate and demonstrative of the real conduct of the genuine structures. The structure is 60 m high and has an arrangement measurement of 20 x 20 m. The auxiliary arrangement of the structure is a fortified cement SMRF framework. Side-long burden opposing components are square RCC segments of size 500 x 500 mm divided at 5 m in both X and Y tomahawks. The floor is a 125 mm thick RCC piece upheld by RCC light emissions 300 x 500 mm. The evaluation of cement for pieces, bars, and sections is M30. 4 quantities of 3D FEM model of the 15-story building has been made utilizing the auxiliary investigation and structure programming A tabs. The chunks have been demonstrated as a membrane component just to move the floor burdens to the shafts. The bars and segments have been displayed as frame components. All the models are indistinguishable and have same stacking and part properties. The principal model is being utilized as a base model for computing the central normal time of the structure and for examination of the outcomes. The pendulum-type TMDs have been added to the remainder of 3 model, with mass proportions of 0.01, 0.02, and 0.04 as recorded in Table 4.2. The TMDs has been demonstrated at the focal point of the structure at the rooftop level, with a direct spring appended to the structure toward one side, and at the free end the mass is relegated. The various boundaries of the TMDs have been recorded in 1.7 Calculation of Tmd Parameters. Based on the modal analysis results of the base model, different parameters of the TMDs have been calculated using the guidelines mentioned earlier in section 3.2.3. The calculated parameters of the TMDs with mass ratios 0.01, 0.02, and 0.04 are listed below in Table 3.